like this, where we have, I think it was a question earlier in the semester, is can you attach elements of different shapes to each other? And yes, you can, and we'll work an example here where we'll do it. So we'll have global node numbers 1, 2, 3. So I'm just ordering the triangle in order. But then over here, 4, 5. Okay. And then we'll have local node numbers to each element. 1, 2, 3. For the triangle, we'll call this element 1. And then for the rectangle, which we'll call element 2, we have 1, 2, 3, and 4. All right. So U1 for element 1 we'll say is equal to capital U1. So capital like meaning the global. U2 element 2 is equal to U1, U2 element 1 is equal to U1 element 2, right? So I'm using the local node number here, right? So U2 corresponds to the local node number 2, right? Is equal to U1, the local node number to element 2, right there. And both of those are equal to the global U2, right? U3 element 1 is equal to U4 element 2 is equal to U3, right? And then the last two are just U2 element 2 is equal to U4, U3 element 2 is equal to U5, right? So what we'll do to help us assemble is we're going to use something that we call a connectivity array. I guess we'll call this BC. And the way we develop the connectivity array is we're basically going to write down the global node numbers for each element. So each row of the connectivity array will be associated with an element, and then in that row we're going to write down the global node numbers in the order of the local node numbers for that element, right? So for the triangle, the global and the local are identical, right? Local 1 is global 1. Local 2 is global 2. Local 3 is global 3, right? So for the triangle, we simply have 1, 2, 3, okay? Then for the rectangle, we have local 1 is global 2, okay? Local 2 is global 4. Local 3 is global 5. And local 4 is global 3, right? See how that works? Now, whenever you do have elements that are differing, right? One has 3 nodes, one has 4. In that scenario, your connectivity array will be ragged, right? It's not like a square matrix, right? It's ragged. It's like 3 rows and then 4, and that can cause some issues. Like not all software really supports ragged arrays. Mathematica does, but like if you're using something like NumPy arrays, what you'd have to do is pad that, right? So you'd want to, right here where this, you could basically put like a -1 there or something just to indicate that that's a dummy value and you don't do anything with it, right? Because we're going to expect that all of our node numbers are positive numbers, They either start at 0 or 1 and just increase.
Professor?
Yeah.
Why are the global nodes not marked in a cyclic order? Like 1, 2, 3, then 4, 5.
Well, because I mean, just a choice that I made to label the cyclic of the triangle first,
Okay.
right? But this is a decision. Ultimately, these connectivity arrays are going to come from a meshing software. So, if you have some complicated shape, you're going to use a tool, meshing software, to tessellate it, right? Break it into finite elements, and that meshing software will give you the connectivity array, the local to global node mapping. Okay.
So it could have been something else as well.
Yeah, and the assembly, it would all work out if it's something else. Yeah, it's okay.
Professor, do we
Yep.
use such techniques in unstructured gridding?
Yeah, it would be the same in an unstructured grid. I chose to draw that as a perfect rectangle, but I could have drawn it as like an irregular quadrilateral, and everything will still work. Yeah. All right. So we're gonna work an example in Mathematica, but let's just so what I'm gonna do is I'm gonna say that the element stiffness matrix for the triangle is basically, I'm just going to say K T 11 K T 12 and dot 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 K 33 T for triangle, not to sound like a transpose. Right. So we know we've already developed that. It's a 3 by 3, right? So I'm just not going to write out any of the terms, right? Because it's just a bunch of writing. I'll do it in Mathematica. So K for the rectangle then is 4 terms, right? So it's K11 rectangle, K12 rectangle, dot 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 dot, K44 rectangle. Right there. Okay. And so this element would be multiplying U1 element 1 or triangle. I'll just use triangle, but it's the same as element 1. So U1T U2T U3T. But of course we know that this is big global U1 U2 U3, and likewise this thing multiplies U1R U2R U3R U4R, and this is U2 global U2 global U4 global U5 and global U3. So what we need to do is, when we go to assemble them, do the assembly, adding terms, right? The terms that have the same global, multiplying the same global row variable, then those two terms need to add together, right? So in this case, U3 is like the last row. Well, when we assemble it, those need to add to this, appropriately to the U3 terms in this row. Right? And so, if we do it for this system, for this one I will write out. So now we have, global K is equal to K11 triangle, K12 triangle, K13 triangle, 0, 0, and that's going to multiply U1 over here, so U2, U3, U4, U5. So then here we have K22 triangle plus K11 rectangle. Here we have K, so I'll write parentheses around those, 2, 3 triangle plus K1, 4 rectangle plus K1, 2 rectangle plus K1, 3 rectangle. And then over here, K3, 1 triangle, K3, 2 triangle plus K4, 1 rectangle, K3, 3 triangle plus K4, 4 rectangle, K4, 2 rectangle, K4, 3 rectangle. And I'm just going to go dot, dot, dot because we're going to derive, we'll do it in Mathematica because I want to see you, like, I want to show you how in a computer you utilize these connectivity arrays to put things together, okay? So, back in Mathematica, we have KT, KR, and then connect. Looks like that. Okay. So first thing we need to do is allocate space for our global stiffness matrix. So we'll do that. We'll say K is a constant array of zeros that are 5 by 5. 5 by 5 because we have 5 global unknowns, right? And then I'm just going to say that KE is equal to KT and KR. So I'm just basically putting KT and KR in another array so that I can loop over them. So I'm going to loop. In this case, I only have 2 elements, and probably not necessary to loop, but this is how you would do it in a code. You would basically, the typical way to do it in a code is to, you loop over all elements in the code. So you basically formulate the stiffness matrix and put it into the global, and then throw away the local. Like you don't store the local stiffness matrix, unless it's an example like this where you basically have one stiffness matrix for a rectangle, and then you have all rectangles. Then you could store that and loop over and just plug it in, say A and B, the heights, and because you can compute the rectangular element stiffness matrix in closed form, right, in terms of the width and the height. So then you could basically just loop over them if you had changing widths and heights. You just plug in those numbers each time and put those into the global value. In reality, we actually don't integrate things in closed form. We use a trick called Gauss integration because it's very difficult to come up in an arbitrary or regular, systematic way, like how you set the bounds of integration for an irregular shaped element, right? So it's easy for a square, right? But if you could have an irregular polygon with 4 sides, that's a valid quad also, but it's hard to set the bounds of integration. So what we do is we use basically a master element that's defined on the bounds -1 to 1. And then there's a way to basically transform the irregular shaped element to map it back to the parent element. We do the integration there, and we can show that as long as the mapping between the child element and the parent element is like an affine mapping, then we can get exact integrals by doing this trick. So everything I'm discussing now, we won't have time to give a lecture on, so that's one of the things I'm going to assign as a video to watch over the weekend or before the next class. Okay, but we won't have to implement that because, basically after today and after homework 4, going on and looking at the final project, we're going to use a finite element framework that handles all of that trickery for us, right, behind the scenes. But I want you to at least know what it's doing. Okay, so let's return to the assembly here. So what we're going to do is we're going to just use a looping structure. In Mathematica, we can call that a do loop. And there's only two elements, so we're just going to loop over, from I goes from 1 to 2. And what we're going to do is basically take the connectivity array, the ith entry, that's the first row of the connectivity array, and use that to index into our global stiffness matrix. So that, so the connectivity array for the triangle is 1, 2, 3, right? So what this, in the first time through the loop, when I equals 1, this is going to read K 1, 2, 3, 1, 2, 3, right? So give me basically those parts of the global stiffness matrix, the first row, first column, second row, second column, such. But then when it goes to the second loop, then it'll read 2, 4, 5, 3, right? And it'll index into that, and it's going to then put KE, which initially, right, this is KE, so the first time through the loop, when I equals 1, the connectivity array is 1, 2, 3, and KE is the KT, right, the triangle stiffness matrix defined above. Second time through the loop, the connectivity array is 2, 4, 5, 3, and this is KR, so then that'll get put in there. Right? So let's see what happens if we run it, and then take a look at the global K. So see how that worked? So that's exactly what I was, starting to write out, but those are the rest of the terms. So I'll publish this notebook when I publish the notes. Okay. Let's work in full example. And it's closely related to your homework.